Okay, I guess we're all here that are going to be here. Can you hear me okay?
Yes.
Great. Okay. Thank you for coming, especially after the break. I'm going to be talking about genealogy with the Wolfram Language. It's a hobby that my wife and I have gotten sucked into. It's a great way to kill a weekend. Just by way of a little bit of background, I discovered that the data that are typically collected when you do genealogy can be exported to a file called GEDCOM. And I looked at the structure and I said, hey, I can suck this up into Mathematica and I can do fun stuff with it. So that's what led to this, and it's gotten along to a point where I can actually speak about it. So before we spend any more time on background, let's get into it. And I'll tell you some of the things I've been doing. Okay, so you all read the abstract. There's been a lot of interest in genealogy recently. There's a lot of stuff on TV these days. There's still always the traditional way of doing genealogy. Family trees passed down in the families in the family Bible or things like that, or you get to a reunion and somebody puts a big piece of paper on the table and everybody writes where they are on that particular branch. My family had one like that about 25 years ago, and they did that, and I had completely forgotten, and my dad went down to the basement last year and pulled out between the rafters this great big piece of craft paper. It was about 6 feet long and 4 feet wide with a huge family tree on it with everything on it that they knew about. And the people filled in the extra stuff that had occurred that other people didn't know. And that's been one of my resources for working on my family tree. And then more recently, there's a new technology is coming along. Besides the traditional record keeping, we now have DNA data, genomic data to help with this. It doesn't get you down identifying that you're related to this person and that person, but it identifies something longer term where your ancestors came from throughout the world, different populations and things like that. Okay. So why do it in Wolfram Language? Well, I didn't want to reinvent things like Ancestry.com or Family Tree Maker or things like that. And what I originally wanted to do when I was doing the genealogical work was I discovered that a lot of my ancestors, grandparents, and their brothers and sisters and things like that were living in similar neighborhoods close to each other in the city of Buffalo, New York. And I was wondering, well, did they get married because they were geographically close? Can I map them? And I took a look at trying to do some stuff with Google Maps, and I couldn't figure out their API, and it fell away. And then I, started working with Wolfram Language with it, and yes, you can do that. So that was the original justification for trying to do something quantitative with the data. And then I decided I also wanted to do things that you couldn't do with the typical software. Usually, you work with one tree, a single tree, and you can't merge trees. And that's a typical problem with genealogists, because when they're working, trying to work out a tree for a client, they'll have a main trunk of the tree, but then there's another group of people that they think might be related, but they're not sure. So they work with them in a separate tree. And then they find the link and they have to glue them together, and that's not always easy. And they're doing the reverse. Taking trees apart is also not easy. You have to make a copy of the tree and delete half the people from one and the other half from the other. And that's not nice. And one reason that I wanted to do that is that traditionally genealogists do not store information about living people in trees for protection of privacy. So I had trees that had my generation in it, my kids' generation, my grandkids' generation in it, and I really didn't want that in Ancestry. So I wrote something where I could export, you can already export the tree into this GEDCOM format file. I pulled that into Mathematica, I broke the tree apart, and then uploaded back the deceased portion of the tree that I can work with, and then I keep the living portion locally on my laptop as a GEDCOM file, and then when I want to work with it, I pull it up, I import it, work with it, add stuff to it, export it, delete it, and that way I don't leave any traces, I hope, around that would compromise anybody's personal information. So the benefits with the summarized functions that I wrote, because you don't want to just look at the raw data. You want to put it together in a cohesive fashion sometimes. It does help me identify mistakes that I've got in my data because I can see, for example, all the residences or all the occupations where somebody was. And I can quickly spot errors where things are out of line, mistyped, things like that. Then I can go back to the original source and correct them there. Also, the code that I wrote that imports the data, I have to do rigorous QC on it because not all of the information pointers within the data are correct. Sometimes it's supposed to be a doubly connected tree in both directions, from individual to family and family back to the individuals. A lot of times only one of them are present. And then sometimes you get people that disappear from the tree because their connections to the family get lost during some editing that the person was doing. And while the individual is carried along in the file, you never get to see them in the tree in the browser. So we've discovered some people that got lost that way. So that's been an advantage of doing it. And lastly, the code that we have, by using the built-in graph functions in Wolfram Language, I can handle things that are called cousin marriages much better. And this is where you get a grandparent that have children, and then they have children, and those children are cousins to each other. And if they get married, then you've formed a loop, a closed, it's not strictly speaking a cycle because this is a directed graph. But oftentimes the commercial software doesn't render that at all. And in Ancestry, for example, which is where I work, they actually make 2 copies of each person in that last union. And then you're wondering, Mr. Smith and Mr. Smith and Mrs. Smith and Mrs. Smith, who's who and where do the kids go from that union and things like that. It can be a real mess. So, okay. So, okay, a little bit of graph theory. Quiz time. Can you see these pictures okay? Should I make it a little bigger? I think we can afford that. Okay. Here's the family tree. Okay, we've got one individual here, another one, and more descendants and more descendants. So what kind of graph is this? Okay. I think I heard somebody say tree. Yeah, it's a tree. In fact, it's actually a directed tree because it goes from one node to the next in one direction. So it's a directed tree. Okay, so here's another one, a little more complicated, a little more realistic. Okay, we've got individuals that are the boxes. We've got marriages or unions, families here that these dots between them. Here's a person that had 2 different spouses because he was widowed. Here's a parent that is missing his spouse, but there are 2 children that we have information on. So this is much more realistic. So what kind of graph is this? Okay. Here it is depicted with graph plot. Okay. Same information. It's a directed acyclic graph. Okay. And they're also bipartite. Because when you include the families in them the way I do here with these extra little nodes, okay, you end up with the families being in one class of vertices and the individuals in the other class. And this is a characteristic of all family trees, that they are bipartite directed acyclic graphs. Okay, the last one here. Here's one. This is one that has a cousin marriage in it. Okay, so we've got some cousins here, Mary, Arden, and John Shakespeare got married to form this family here, and William Shakespeare was one of their children. So what kind of graph is this? Okay. Again, it's a directed acyclic graph. It's acyclic because of the edges. There's no way you can get from an individual back to that individual's ancestor. So it's still acyclic, even though it looks like there's a closed loop in there. It's also bipartite. And here is the example showing we've got William Shakespeare here, and we've got William Shakespeare over here, and we've got Joan Shakespeare, his sister, and Joan Shakespeare here, his sister, and Margaret. So it gets really confusing as to knowing what to do here. So this is why I like doing it with real graph software Okay. So what is GEDCOM exactly? GEDCOM is, it's an acronym for Genealogical Data Communication. It was developed by the Church of the Latter-day Saints, the Mormons, because they have a mandate to work out the genealogies of their members. The members are responsible for doing that. And so they've got all of this infrastructure in place to do it. And what's really great, they've got a website called Ancestry.com, which has not all, but it has an enormous amount of data that you can search and use to validate the information in your family tree, such as the US Census, city directories, all kinds of things that you can use. So this file is actually, it's a grammar, and each line looks like this. There's a level indicator and then a delimiter, and then you may have some optional information, or an external reference plus a delimiter, and then a tag, which is a key thing, and then possibly a value, and then the end of the line, okay? So again, it's just 4 parts: a level, a reference ID, or a pointer actually, a tag, and a line value. Okay, the delimiters are spaces, the terminators are new lines. Okay, the level that's used here at the very beginning is what determines the hierarchy in the data. Okay, so here we have a simple tree. You probably know this family, Abraham Lincoln and his wife Mary, and their 4 sons. And this is the corresponding GEDCOM file for it. Okay, and we can see here we've got the levels here in red. We've got the external reference IDs here in blue. We've got the tags in green, and then we've got the values out here in the magenta. We can look at a single individual entry in the file. Here's one for the first individual, and we've got information about the death, and then okay, so about the individual. We've got the death and the birth and the gender, okay? And then in the death, because at level 2 now, we've got the date and the place. And similarly for birth, we've got date and place. Gender doesn't have any derivative information. The name doesn't have any derivative information. They have marked up the surname with slashes, so you can identify that clearly, which helps. And then we have a reference to the family for this individual, that this individual is a member of family F1. Okay, and then we have family information in the file as well. So here's family F1, and the husband is P1, the wife is P6. There's a child, P5, who was a natural child of both the father and the mother, and so on. And then we have information, additional information about this family, about its marriage, with a date and a place as well. Okay. So there are hierarchies also, as I mentioned, and in the individuals, so here's the individual P1 again, Abraham, and here it is in the linear notation that they use in their file, but this is the tree structure, the hierarchical structure that actually represents. And this is why it's so easy to get it into Wolfram Language. And then the same for families, okay, here's the linear notation that they use, and then here, because of the levels, we see the information, level 0, level 1, level 2. Okay. And then all the tags that are used, there are lots of them. Most of them are well-defined in the specification. There are what are called program-defined tags as well. They begin with an underscore. So you're not restricted to just the standard set. You can extend it. And that then lets one represent any kind of hierarchical information in this file format. And in fact, there's a link down here, for example, for different human languages as well as computer languages that have been stored in the GEDCOM format. So you can see how the different languages evolved, both human languages and computer languages. Okay, so decision time. I can't possibly fit in everything that I could in this talk. So do we want to take a road to the left or to the right? Do we want to look at applications, or do we want to look at the implementation aspects? Your choice. Nodding your head means what?
Implementation, first one.
What's that?
The implementation.
Okay, we'll jump to the implementation first, and then we'll come back and look at the applications. Okay, this is a technology conference, so we're allowed to do this. I'm being a bad mathematician because I'm showing you how I do my tricks. The data, I store the data as a set of lists, essentially as down values of these symbols here in the package. And I also maintain a list of all the family trees so that I know how many of these lists that I have. Each of these lists, for example, the persons are lists of individuals. The individuals themselves consist of a pointer, a reference back to the family tree to which they belong, and then their properties. Families have a similar structure. Okay? Properties are also hierarchical. They have a description string and then a list of subproperties. And the subproperties have the same structure as properties, so it can just keep going as needed. Okay? And then the way you find the connections in an individual, there are pointers back to the family where the person is a child in the family, and there are also pointers back to other families where that person is a spouse. And so the one set of pointers, the child to family pointers, point up the tree, and the others, spouse to family, point down. And then families have pointers to the husband and wife, and also to the children, and they also have in them other properties, as we saw, such as marriages, the date of the marriage ceremony and things like that. One thing that I've done to keep the processing relatively fast is that dates, because when they come in from the external source, can be in any format. So I use date list to take that string and get a date list back. And if I get a valid date list back, then I put that inside of an interpretation to use, so that it displays as what was originally in the data, because I try to be faithful to that. But I still have something I can compute with, which is the date list itself. Okay, so let's load the package. And we can look at some of the things that it can do. I've got functions that can read the gedcom file. We can read files off the desktop, or we can take them from the web if you've got a URL. And some utility functions, to test if a given name is one of the trees that I've got in memory. The one thing that Ancestry can let you do, you can build lots of family trees in Ancestry. My wife has about 16 of them that she's working on. But you can only look at one at a time, and they don't talk to each other. But in Wolfram Language, I can read in several family trees and work with them simultaneously. That's what lets me glue them together, take them apart, and things like that, or do comparisons between them. Because I've got several in memory, they are in memory, and we don't pass them around the way we do traditional data objects in Wolfram Language. If you have an array, you pass the whole array. You're not passing a name about it. Here we're actually working with the names of things, because some of these trees can get very large, and if you've got them in a notebook, your notebooks get very big and unwieldy. So we work with the names of them instead, and so we need something to set the name for the current family tree. So let me read one in. Okay, I read in this file Anderson family tree, and I gave it the name Anderson. I can get a summary of it using the summarize family tree function. And here it gives a quick summary: the number of individuals, the number of families, the number of sources. These are the sources in the source data that came in with a file about, this person lived in 1910 at this street. They were the head of the household. That came from the census. So the census reference is stored in the source. And that information about that residence with the individual points to that source citation. So that's what that is. But from this information, I can compute the number of generations, and I can compute something like cousin marriages. So these are things that a genealogist would be interested in that are pretty easy to compute from the graph structure itself. So they're there in the summary, and then some information about where the data came from. This came from Ancestry.com, family trees, with the version 2010.3, et cetera. Okay, we can also draw a graph. And this is using the built-in function graph. All I do is assemble a list of vertices, which are the individuals and the families, and the edges. And I've color-coded them here and put tooltips on them so you can see who is where in the tree. So this is Edward Anderson at the top of our tree, and here's the family he was in, and here's one son, and here's another son, and so on. We can work our way down through the tree. You can also see the bipartite structure because we've got individuals at one level and then families at a level, individuals, families, and so on. We've got functions for working with individuals. You can have more than one John Smith in your tree. My wife is Irish, and she has 1 million Thomas Mulrys in her family. Not quite 1 million, but several. So you can't just say, Thomas Mulry and get the one person you're actually looking for. So I've written a function called find individual that at the very least takes the surname and then returns all the possible responses for that. And you can completely wildcard it and find all the individuals in your tree, which in this case is not bad. And I'm using an entity-like object to represent them in the notebook. It makes it it makes it much more compact than the raw individual object. And it quickly lets me know, as a genealogist, who I'm dealing with. I can tell the gender quickly. I've got the person's name. I've got their dates of birth and death. And I can easily look at this and compare it to another Gertrude Abercrombie that I might have and know if it's the same person or not. Okay? We can look in more detail about all the information about a given individual by using the show individual function, their name, gender, which tree they're in, their parents, siblings, their spouses, the children by each spouse. If this person had been married more than once, we'd have additional entries over here for them. And then the list of the events that were in the data as well. Okay, and we can do a similar thing with families. Okay, so here are all the families in the tree, and we show the surnames of both spouses, the marriage date, and the number of children. And this helps disambiguate which one is which. And we can copy them and paste them into functions, for example, down here to actually work with them. Okay, and we can draw a more traditional type of family. One thing that I did not try to bite off for this was trying to draw a family tree like this with lots of generations in it, because that's a hard problem, especially the layout to minimize crossings and things like that. And the commercial software doesn't always show you all of the individuals. They show you a subset around the individual you're interested in. And they have some algorithm for that, and it's not perfect. And I didn't want to bite that off. So this much I can do easily, and this is one of the workhorses along with the family tree graph function. Okay, so the algorithms, I do make use of a lot of the built-in functions for graph theory and graph computation, directed edges, graph, undirected graph, so I can take a directed acyclic graph and make it undirected so I can do certain types of computations on it. Edge counts, vertex counts, and connected components are also very important. And if we have time for all the applications, which we're probably not, we can see some of those. Here's the family graph again. I can get vertex counts. I can test if it's bipartite, and yes it is, and it's directed, and it is acyclic, but it's not a tree. Okay, it's not a tree graph, and that's because there is not a unique root. I've got this person that could be a root, that one, this one, this one, this one, so that's why it's not a strict tree. Okay. Let's see. There are a number of different places I need to go with it. I started this work under version 7 of Mathematica. We didn't have associations then. We didn't have entities. If I can get a real entity type implementation, then I can do things like treat an individual or a family as a function. So I can say, use family as a function and say, give me the wife property, and it would then return an individual. And for an individual, I could say, give me the birth property, and that would give me the birth. And of the birth object, I could say, give me the date or the place, and things like that. I've got lots of functions, and a lot of them are things like get children, get death date, get descendants. All of those can be replaced with this idiom. So this is where I want to go next. Okay, and I've got some graphics functions for drawing them. Okay, so I've got a few minutes left. I want to show you quickly some of the applications. Let's see. We can skip over that. Okay, we can do pedigrees. So here's that tree again, and we're going to focus here on George Anderson. Okay, and we can get his ancestors here, and we can draw them. And so here we are, here's George, and here are his ancestors, each by generation. We can do a similar thing with descendants. And here's George, and now I've drawn it with the root to the left, so his descendants go to the right. Okay. Family relationships. This is some real computing done on family trees. So here I'm going to show that tree again. Okay, so here's the tree as drawn in Ancestry, and here's the graph as drawn in Wolfram Language. Okay, here's George, and I believe, let's see, George, where's George? Here's George over here in the tree. Okay, we can actually compute relationships. Okay, so these two individuals, Bruce Johnson and Alice Johnson, Alice is the sister to Bruce, and we can do it the other way around and find out that Bruce is the brother to Alice. Okay. And then we can also do something which is, I think, really kind of fun, is we can look at all the individuals in the tree, and we can pick, yeah, okay, this one was, it randomly picks two individuals to start, and it shows the same person for both times. So let's just pick another one here. Okay, so it shows the relationship in the tree, and it says that William Anderson is the nephew of Thomas Anderson. And, we can do all of them. I'd like to be able to turn this around so I can click on an individual here and another one over there, and it will show them in the list on the left and then tell me what they are. But it's got all of them in there, so I can find out first cousins twice removed and things like that. And if I can deploy this to the cloud, then when I'm at a cocktail party and somebody says, no, she's your second cousin, I can whip this out and say, no, she's really my first cousin. And settle those arguments with my wife. She keeps this all in her head. I have to see it on paper. Okay, we can also compute consanguinity, in other words, blood relationship. How many degrees are you related to somebody else? And there are two kinds of that. There's civil law consanguinity and common law consanguinity, and they compute it slightly differently. So I've got both of those implemented, and so for these 5 individuals, we can see, for example, that Paul and Christina here are second degree related. It's lineal, direct relationship, and I'm also showing that that Christina is the granddaughter of Paul. In this case here, Jane is 4th degree related to Christina, and they're first cousins. Okay. If there isn't a common name for the relationship, I just say unknown. Okay. And then we've also got common law consanguinity, and I won't show that table. And then, this one's fun here. Okay, we'll read in my family tree, and we're going to look at my grandfather. It takes a little bit to read this, and I've got almost 500 people in the tree, deceased people in the tree. This is how I'm getting close to the entity-like capability with the get property function. Come on. Okay. So a lot of individuals, it looks like I've got a cousin marriage, and I have to look that up because I don't remember it. Also, you'll notice now that we have more than one family tree in memory, it now tells me which tree the individual is in to help keep things straight. So let's get a list of all the places that he lived. There are 28 different residence entries in the data. I can use the geocode function, which is in the initialization package for the notebook, so it'll be available to you there. We can go out to Google and get the coordinates, the latitude and longitude of each of these locations that are a street address, a city, possibly a county, a state, and the country. Okay? And here are a handful of them drawn randomly. from that set. Yep. Oh, come on. Okay. And we can map them. So this is one of the things I wanted to do. Okay, so here's the map of where my grandfather lived. We can zoom out to give you the context. It's here in Buffalo, New York, in the eastern United States. And we can zoom back in now, and almost at the street level, we can see that this is where he was born in 1898, and that they lived there about 5 years, because he was present in the US and the New York State Census. Then they moved here and here, over here, and then up to there. Then they went way over here to Batavia, New York, and then down to East Aurora, and then they moved back to Buffalo in the Kenmore neighborhood, and then over here to Williamsville. And this is where I first knew them, at their last house where they lived the last 30 or 40 years. So you can do some fun stuff like that with Wolfram Language, which is really nice. I'm out of time. I'm over by a minute. I've also have in here working with timelines, taking the same kind of data and producing a timeline with a timeline function. Ancestry is starting to do something like that, but I don't think it's quite as nice as what we can do here. And of course, the data are all computable. So it's just a start to the fun things you can do or the more serious things you can do with the data. And with that, I will thank you for your attention. And just catch me anytime this week if you've got questions. We don't have time for them now. So thank you.